Welcome to the world of chemistry. Today we're talking about solutions. And if you recall, the definition of a solution is a homogeneous mixture. And because it's a mixture, it's of various compositions. It could be concentrated or dilute. So what we mean, here's an example of a solution. Very typically you go into a chemistry lab and you see bottles with labels on them. The particular label on this solution says 3M, which means molar, H2SO4, sulfuric acid. So this is a homogeneous solution of 3 molar sulfuric acid. So I want to look at the idea of a solution and try to describe these solutions. For instance, I have 3 beakers here. And you look at them and they just are clear. You don't see any difference at all between these beakers. However, one of these beakers is saturated, another one is unsaturated, and the other is supersaturated. Okay? And so I want to demonstrate that a little bit. So unsaturated means it doesn't have as much solute as it can hold, that will dissolve. Saturated means that it has all the solute that it can possibly hold, and supersaturated means that it has more than it can hold. And you say, well, how can it have more than it can hold? Well, it's a condition, for instance, like a cloud. It may not rain. You have to form nucleation to get it started. So there's a simple way to do a little test. The solution that I have is sodium acetate. And what I have is a few little crystals of sodium acetate. Okay. And if I put a few crystals into this one, and we stir a little bit, what you see is the crystals on the bottom are disappearing. It is dissolving. So we no longer have those little bit of crystals. It's completely gone, those crystals I put in. Which means then that this solution was unsaturated. I dissolved some more into it. Put a few crystals in the next one. And they're settling to the bottom. Put a few more just so you can see them. And I'll stir them. And every time I stir them, they settle out and they remain there in the bottom. So this means that this was saturated. No more can dissolve. And then my next one, put a few crystals into this situation and see what happens. You can almost see a trail of the number of crystals as I stir this. Oh my goodness. Do you see what's happening? All of the extra crystals are settling out, and I'm getting a very, very many crystals, completely cloudy, completely filled with crystals. So that clear solution, by adding a few crystals, I began the precipitating process, and that indicates that was the supersaturated. So a simple test to see if a solution is unsaturated, it means that it will dissolve a few crystals you put in. If it's saturated, it means the crystals will just settle to the bottom and there'll be no change. But if it's supersaturated, the crystals will start a process which will precipitate out the entire solution. So the next topic that I want to talk about, solutions, how very important and how we can make them up to any concentration that we want, unsaturated up to saturated. So I'm going to show a process here of making a solution. It's pretty well described in our chapter. So let's make a solution of copper sulfate. So this is the information that I have about copper sulfate. The crystal of copper sulfate is copper sulfate pentahydrate, which is something a little bit different. But I'll put a little of those crystals out here for you to see. They're nice, pretty blue crystal. Okay. So I'm going to look on the side of the bottle. I want to make a 0.1 molar solution. So 0.1 molar means 0.1 mole of copper sulfate pentahydrate in a liter, or 1,000 milliliters. So the very first thing I have to do is I have to weigh this out. And as you know, I can't exactly weigh a mole. I mean, I have to know the molar mass. And so fortunately, on every bottle, it tells me on this that the molar mass of copper sulfate pentahydrate is 249.7. So I'll put that down, 249.7 grams per mole. So you can see very carefully, if I want to take 1/10 of a mole, then I'll just move this decimal place over and I'll have to weigh out 24 grams and put that in a liter. So I have to decide how much I want to make. I'd rather make 1/4 of a liter. So I have to take 24.97 and divide that by 4. And when I do that, and I better use my calculator to do that, 24.97 divided by 4 is equal to 6.24 grams. So let's talk about using 6.24 grams of the copper sulfate in 250 milliliters. So it would have been 24.9 grams in 1,000 milliliters, and then I took 1/4 of the denominator, got 250 milliliters, and got 1/4 of that. So to make that solution up, here's the way that I would do this. And I'll just quickly do that for you because it's kind of important. I'll just put one of these on, and I'll tear it, in other words, make it 0 it so that it says nothing is there. And then I will add 6.24 grams of this. 1, 2, 3, 4, 5, 6.24, 6.25, close enough. Okay, so then this will be the amount that we'll have to put into 250 milliliters. Now we have these special flasks. They're very accurate. They're called volumetric flasks. And you can see that this is a 500 milliliter volumetric flask. That is to say that you can raise the level of this up to a mark, and it'll be exactly 500 milliliters. And here's a 250 milliliter volumetric flask. So since I want to do this, I want to put 6.24 grams in 254 milliliters, I will use this flask. And I will do it in this way. Let me put this up here so you can see. So these kind of weighing boats, they work pretty well to make a kind of a little funnel. And I'll just go ahead and put that in there. I'm not spilling. So got most of it in there. And then, so now all I need to do is dissolve that. And the general way in which you do that is you add distilled water, to about half of the amount. And then these flasks are kind of designed so that you can swirl them. They have a top on them that you can invert, dissolve that substance pretty easily. It's nearly dissolved already. So you want to dissolve it and then finally top it off. Okay. So what I have made is a solution. When I finish with this, I will have made a solution that is I pour it in a bottle and I'll label it 0.1 molar copper sulfate. And the blue color is due to copper, so it's not quite done. The mixing has to be pretty vigorous to get it dissolved. And various things. You can put this in. You can put a stir bar in this and make sure it's completely dissolved. What I'm going to do now is to top it off. It's nearly dissolved, but I have to fill it to exactly. There's a mark right up here. I don't know if you can see that. And when I get it exactly to that mark, and I'm going to pour quite a bit into there till it starts up on the mark. And then for the last mark, I'll do eye level. Raise the level to so the meniscus is right on that mark. So there will be my solution of 2 molar copper sulfate. And usually you don't store things in there, so I'll put this into a 250 milliliter flask. And label it to 0.1 molar copper sulfate. Then I might ask myself, so that's how you make up a solution when you start with a solid. You weigh the right amount, convert the moles that you want into grams, and dissolve it to make up a solution. The second kind of solution that you would be making would be by dilution. For instance, I would say that I'd like to make maybe instead of 0.1 molar, I've got 0.1 molar. And I would like to make 0.01 molar. Well, the way in which, and how much would I like to make? I'd like to make 25 milliliters of it. And I would do this dilution formula, 0.01 over 0.1. So this would basically say, I'm sorry, I'm going to make 250 milliliters since I have that flask out of that. So basically, the 0.1 would be, say that I should take 25 milliliters and dilute it up to 24. Okay, my first example was creating a solution by weighing the solid. My second example would be by dilution. And so I've decided, I already had the 0.1 molar, and I decided that if I put 25 milliliters into this and dilute it to 250, I will have cut it by 1/10. And so the way you do that is you use a volumetric pipette, very accurate, and you just would go ahead and you would pipette Okay, so I'm drawing that up and then I'm letting out very slowly to a very accurate mark right there. Transferring that over to here. And it's to deliver. And so once I delivered that in there, then I'll add the distilled water and I'll have 0.01 molar. And it'll be kind of interesting because it also shows you another property, that the darker colored solution are more concentrated. So that's done. Let's do the dilution. Take it actually up to the bottom of the meniscus. Mix it. So there's a little blue. So I've made two solutions of copper sulfate and showed you how to make it from solid in a volumetric flask and how to do a dilution of that particular solution. The next thing I want to talk to you about is conductivity. Okay, I have an apparatus here which is it's plugged into the electricity, and the light bulbs will light when the current is flowing. If it's not flowing, they will not light. And so basically, when these both touch, actually the electricity is going through the metal of the scissors back to the other side. So in order for these light bulbs to light, you have to have a way for the electricity to come from this anode over to the other. You have to make them connected. And so the only way that will happen would be, here's your one electrode, and it's got electrons on it. And here's the other, that's positive, and that's negative. And these electrons have to somehow or other travel over there. I could easily make them travel over there if I put a piece of copper wire or a piece of metal, connected them, then the bulb is lit. So what I'm going to do is I'm going to test this conductivity in a solution. Now, if I have a solution and it has positive ions and negative ions, all this has to do is this positive ion has to come up here and pick up an electron, and this negative ion has to go over there and deposit an electron, and I have, in effect, let an electron go through the solution. So the conductivity of a solution is going to mean how many ions are present in it. So I'll start here with a solution. I will start with distilled water. Now, distilled water is, in reality, not supposed to have any ions in it. So we put that in there, and you see nothing. Okay? So it is a non-electrolyte, distilled water. But let's go to something like sodium chloride. Now we know that sodium chloride is dissolves as an ionic bond between it, and when it dissolves in water you get sodium ions and chloride ions. And so we just test that out, and there you see the sodium chloride. Okay. Let's try a substance, so let's say like let's try a substance like, try this because this is when I dissolved the sodium acetate. This should have tons of ions. Remember, this is saturated. Oops. Gotta get them. Well, that's distilled water. This is the distilled water. The other one was the saturated. I don't know if I want to do this or not, but there you go. Lots of dissolved iron. Ooh, let's rinse that off. Don't worry about that. It's a little salt water. Okay. But I want to show something else. Here is sugar water. Now we know that sugar is not an ionic compound. So I have sugar dissolved in this water, and guess what? There are no ions. So sugar water doesn't conduct electricity. We have some things that are strong electrolytes and some things that are weak electrolytes. For instance, strong acids, like hydrochloric acid, are strong electrolytes. Weak acids, like acetic acid, are weak electrolytes, because an acid has to have hydrogen ions. And so if it's a weak acid, it produces only a few hydrogen ions. So we're going to look at acetic acid. And what you see is very faint glow in the one bulb. So it's a weak electrolyte. Sodium chloride was a strong electrolyte. Sugar water was a non-electrolyte. So this gives us a clue to a little bit of what's happening inside of the various solutions. In this chapter on solutions, the very last part of the chapter talks about a properties called colligative properties. And we're not really going to go very much into the mathematics of it, but they're important properties of solutions. And let me just make a list of the colligative properties. The colligative properties are called this because they depend on the number present, like a collection. And so therefore they are freezing point, lowering. If you have a pan of water outside and the temperature drops to 0 degrees, it will freeze. If you put some salt in that water, then the presence of those salt particles will lower the freezing point, and it'll be not freeze at 0, but lower temperature. We have boiling point, elevation. Sometimes if you're in Colorado and you want to put your food and cook it in boiling water, well, water boils at about 80 degrees or 90 degrees there at a lower temperature than normal because of the high altitude, because anything boils when its pressure reaches the atmospheric pressure. You can put a little salt in that water, and that'll elevate the boiling point, and that'll hasten you to cook your food. And then the other one is osmotic. And this is an important one for life science. You have two solutions separated by a semi-permeable membrane, and only the water or the smaller particle can pass through the membrane. And so what will happen is that the water will go into the more concentrated solution, attempting to dilute it, and the level will rise. So you can look at the details and pictures in your book. But for this is our first kind of discussion, and wanted to show you a few things about solutions and why they're important in chemistry. Thank you.